Hey there, my name is Ross Beardsley, and I work for Ramble in our Novato, California office. My talk today will cover Revision 5 of the Carbon Bond 6 mechanism, or CB6R5. I will start by providing a general overview of the Carbon Bond 6 mechanism and its development over time. Then I'll discuss our approach for this revision of the mechanism, and then finally I'll present some model results to show you the impact of the mechanism updates on model concentrations of air pollutants and model performance. First, I want to acknowledge and thank the state of Texas who funded this mechanism update through the Texas Commission on Environmental Quality, or TCEQ. The content and conclusions presented here are our own and do not necessarily represent findings, opinions, or conclusions of the TCEQ. The carbon bond 6 mechanism, or CB6, is a condensed chemical mechanism that represents the chemistry of volatile organic compounds and oxidants in the troposphere. As it is a condensed mechanism, it does not attempt to explicitly represent the huge number of reactions occurring. Instead, CB6 groups volatile organic compounds and radicals according to the molecular structure. For example, CB6 has a model species to represent ketone functional groups and another to represent the paraffin carbon bond. Therefore, a ketone such as octanol will be represented in CB6 as 7-par and 1 ketone. Condensing the mechanism in this way makes CB6 suitable for 3D atmospheric models such as the photochemical model CMAS, where computational efficiency is of the utmost importance. The mechanism does treat some species explicitly. When doing so is important for accurately characterizing gas phase oxidation or the production of fine particulate matter. A couple of examples of explicit species are propane, which is one of a few long-lived VOCs that are important to ozone production at regional scales, and secondary organic aerosol precursors such as glyoxal that produce SOA by aqueous phase reactions. The first version of CB6 was released in 2010 using data available through the middle of that year. In 2013, CB6R2 was released, which introduced heterogeneous reactions of organic nitrates to form nitric acid and updates the reactions of isoprene and aromatics. CB6R3 was released in 2015 to better represent wintertime high ozone events, and this is the current version in the US EPA's CMAC model. Then finally, CB6R4 was released in 2016 to account for ozone depletion in the marine boundary layer and was updated in 2019 to include reactions of dimethyl sulfide. Therefore, although CB6 is revised many times over the years since its release in 2010, the core inorganic reactions of NOx, ozone, and the hydroxyl radical have not been updated since the initial release. Updating these core reactions was the primary motivation for this work. In this update of CB6, we prioritized the review and update of the mechanism in a few ways. First, we used the top 50 parameters in CB6R4 that were determined to contribute to uncertainty in ozone predictions. The parameters contributing to ozone uncertainty were identified in a recent study by Dunker et al. 2020, in which a detailed sensitivity analysis of CB6R4 was performed with a decoupled direct method. This study estimated the uncertainty due to all rate constants and stoichiometric parameters in CB6R4, in addition to the uncertainty caused by emissions, deposition velocities, and boundary conditions. We prioritized the top 50 parameters contributing to this uncertainty in our review of CB6R4. Next, we prioritize reactions involving nitrogen oxides, hydrogen oxide radicals, and odd oxygen radicals. And then last, we prioritize reactions of simple organic compounds, such as simple alkanes, and SOA precursors, such as benzene and toluene with oxidants. Our overall approach was to review the current data on these reactions and determine if the updates to CB6R mechanism were needed. The primary data sources we used in performing this update to CB6 were the reviews produced by the International Union of Pure and Applied Chemistry's Task Group on Chemical Kinetic Data Evaluation, and the reviews by NASA's Jet Propulsion Laboratory Panel for Data Evaluation. These panels continuously review new scientific literature and provide recommendations for many, but not all, chemical reactions. CB6 mechanisms in the past have generally relied more on the recommendations from the IUPAC panel than those from the JPL panel, and this remains the case for the CB6R5 updates. However, we consult both recommendations and use the JPL recommendations where it's found to be appropriate. Now to summarize the updates that were made, 152 reactions were reviewed for the update from CB6R4 to CB6R5 based on the priorities I discussed on the previous slide. This review resulted in 47 reaction rate updates due to new recommendations or data being available from IUPAC or JPL. Of these, 41 of the updates were for rate constants, and the remaining 6 were for changes to phospholysis reactions, with changes to formaldehyde, acetaldehyde, and higher aldehydes, glyoxyl, and glycolaldehyde. Of these rate updates, the largest was phospholysis with glyoxyl, which increased by approximately an order of magnitude. And the largest rate decrease was for that reaction of glyoxyl and the nitrate radical, which decreased by nearly an order of magnitude relative to CB6R4. We also added one new reaction, which I'll discuss in detail in the next slide, but did not add or remove any model species. As we did not add or remove any model species, there are no changes required for emission inputs or boundary conditions. There were also a number of changes to reaction products, such as the reaction order or reaction product yields. If you want to look at the full listing of changes, you can find the full report on the TCQ website, which I have linked at the end of the presentation. One of the most important reactions that we reviewed was the reaction of the hydroxyl radical OH with NO2. This reaction was ranked 8th in the top 50 parameters that contribute to uncertainty in ozone predictions in Dunker et al. We reviewed the current IUPAC and JPL recommendations for this reaction and found they were substantially different, with CB6R4 using the current JPL recommendation. We supplemented this review with new research from Amidro et al., in which the authors provide new laboratory measurements for this reaction and analyze this new data in conjunction with the previous published studies, much like the reviews published by IUPAC and JPL. This study recommends a rate constant in between the IUPAC and JPL recommendations, and also found that measurements show that water vapor accelerates the rate of this reaction due to water vapor being more effective as a third body than nitrogen or oxygen. This results in an acceleration of this reaction in humid regions such as the Gulf of Mexico and other water bodies. Due to the lack of consensus among the recommendations for this reaction between IUPAC and JPL, we decided to retain the current JPL recommendation, which is used in CB6R4, in this mechanism update. We also wanted to account for this new finding of Amidro et al. That shows the acceleration caused by water vapor. To account for this effect, we implemented a simple reaction shown here at the bottom of OH plus NO2 plus water to form nitric acid and H2O based on the measurements in that study. This is in addition to the existing OH-NO2 reaction, and this consumes OH and lowers the OH concentration, more so where humidity is high. This reaction also consumes NO2 and consequently tends to lower ozone concentrations. Lower ozone reduces the amount of OH produced by the OH phospholysis and thus lowers the OH concentration, and thus this acts synergistically with direct OH removal by the added reaction. Following the revision, we performed a series of runs with the CMAS photochemical grid model to test the new mechanism and determine the impact of the updates on the concentrations and model performance of important atmospheric species such as ozone. The modeling period we selected was a period of high ozone in Texas in June of 2012. And for the modeling, we used the TCEQ modeling platform with the newest version of CMAS version 7. Overall, we performed 9 simulations to isolate the impacts of updates for important groups of chemical reactions, such as the photolysis and the OH plus NO2 reaction I was just discussing on the previous slide. And we also applied the chemical process analysis probing tool to give us more information on how the chemical reactions were influencing model species concentrations and the production and destruction of ozone and other species. Today in my talk, in the interest of time, I will be showing a small subset of results that focus on the larger US modeling domain. However, a full discussion of the results for all the modeling domains and chemical species and the runs that we did can be found in the full report, which is available on the TCEQ website and linked at the end of this presentation. Now to get to some results. Here on the left, I'm showing the absolute ozone concentrations across the modeling domain produced through the use of the CB6R5 mechanism, and on the right, the difference between the ozone produced by CB6R5 and CB6R4. The results shown on this slide and across all slides are average over the hours of high ozone from 11 a.m. to 3 p.m. During a period of high ozone in Texas in early June. As can be seen in the right figure, CB6R5 increased ozone production during the high ozone period modeled relative to CB6R4 over Texas and the majority of US, with most changes ranging from 0.3 to 3 ppb. As I mentioned, we ran a number of sensitivity tests to determine and isolate the impacts of changes to important groups of chemical species. These sensitivity tests revealed that the updates made to photolysis reactions, peroxyacetyl nitrate reactions or PAN, RO2 reactions of the peroxy radical tend to increase ozone concentrations, while updates to the ozone plus NO reaction and the OH plus NO2 plus HO2 reactions tend to reduce ozone. On this slide, I'm showing results in the same format, but for nitrogen dioxide. For nitrogen dioxide, there are small increases in concentrations over land relative to CB6R4, as you can see on the right, which can result in some increases in ozone and NOx-limited areas. However, over water bodies such as the Gulf of Mexico, as you can see on the bottom of the slide on the right, and some rural areas, the changes in CB6R5 result in decreases of NO2. This is largely due to changes in the reaction rates of peroxyacetyl nitrate and related species, and also the added OH plus NO2 plus water vapor reaction I talked about previously. This is particularly true of the Gulf of Mexico, as you can see, and other humid areas. In addition to the concentrations we looked at for the CAMX host model outputs, we also plotted outputs from the CAMX chemical process analysis probing tool. These results are average over the same time period as for the species concentrations. This was to help us understand how the CB6R5 mechanism updates influence changes in species concentrations. CPA information is fundamentally different from CAMX concentrations in that CPA parameters are not transported between grid cells by advection and diffusion. Thus, maps of CPA parameters, such as the ozone production rate I'm showing on the left here, can reveal differences between neighboring grid cells that are difficult to see from concentration maps because of the transportation between these grid cells. CPA information for ozone production and destruction rates are shown for the same periods on the left and right, respectively. On the left, stronger ozone production is strongly associated with emissions from urban and industrialized areas. Here I'm showing the difference between CB6R5 and CB6R4 ozone production from CPA. And the CB6R5 updates tend to reduce ozone production in urban areas, as you can see in the map, but increases ozone production in more rural areas. For the periods shown, most of the regions classified as VOC limited see decreased ozone production rates after these updates to the CB6 mechanism. On the right, I'm showing the difference between ozone destruction from CB6R5 to CB6R4. Photochemical reactions can destroy ozone simultaneous with this ozone production. The CPA parameter ozone destruction shows that the CB6R5 updates lead to more ozone destruction over the Gulf, but less ozone destruction over land. This reduced ozone destruction generally contributes to higher ozone concentrations over land with CB6R5 compared to CB6R4. Although not shown here, increased ozone production results in elevated ozone OH concentrations due to photolysis of additional ozone. Lastly, we also quantified impacts of the mechanism updates to ozone model performance by comparing the model 8-hour average ozone from 11 a.m. to 7 p.m. for each day in June 2012 to observations from the continuous ambient monitoring stations in the East Texas modeling domain. We computed statistical metrics following recommendations of Emery et al. A comparison of the metrics we calculated for CB6R4 and CB6R5 are shown in the table here. Overall, model performance for ozone was similar for both mechanisms, with the tendency of CB6R5 to protect higher ozone than CB6R4, resulting in a slightly more positive bias. Here you can see the mean bias for CB6R5 for this period was 5.8 ppb for ozone compared to 5.4 ppb for CB6R4, and a slightly larger error. Here you can see 8.1 ppb compared to 8 ppb with CB6R5 and CB6R4. In the paper by Emery et al., they provide model performance benchmarks for normalized mean bias, normalized mean error, and correlation coefficient that include goals that represent the best the model can be expected to achieve, and criteria that represent what most past modeling applications have achieved. Both mechanisms, CB6R4 and CB6R5, meet the criteria for normalized mean bias and normalized mean error, and the goal for the correlation coefficient, as can be seen in Table 6. As I mentioned, the full documentation on the updates to CB6R5 can be found on the TCEQ website. And then lastly, CB6R5 will be implemented in the next version of CAMX, which is version 7.1. Please, I highly recommend going to see Chris Emery's presentation on the recent updates to CAMX and all the new great capability that's available. Thank you. That's all I have, and I look forward to answering all of your questions.